This is going to be nanotechnology for spine surgery. We have two orthopedic surgeons. I'm going to give a brief introduction into the product and into the science, and then I'm going to turn it over. And we have a neurosurgeon and an orthopedic surgeon that will go through some cases and show us some of their results. Let me have the first slide, Paul. Okay, so our product is Nanobone synthetic bone graft, and we feel it's a clinically proven, cost-effective replacement for I'm going to say all other bone graft materials. We have, before I get into exactly what it is, I'm just going to state we have two forms. We have Nanobone SPX putty. In that applicator, this is basically used. I think this is used a lot in spine surgery for more or less open procedures and void fillers. And our indications are is bone repair, indicated as a bone void filler. That no need to add. Importantly, we don't need to add blood, bone marrow, aspirin, or other materials, even in spinal fusion. So it's pretty much a standalone product. Because of the a lot of minimally invasive indications and usage now, we came out with the Nanobone Qd, which is an applicator which allows you to put a more precise amount into a place where you need it. The handling characteristics are very good. It stays where you put it. It does not wash away with blood. And this device is mostly used where you might want to do minimally invasive or for whatever makes you feel better or eases your your surgical technique. Can I have the next slide? And before I get into the actual the product, I just want to say, so Nanobone was developed in Europe. It was used extensively in Europe, mostly at first for dental applications. It was found to be very efficacious. It was brought to the United States and commercially available here since 2015. And we've been getting over the years we've built up quite a lot of usage, and I'll explain a little bit now about what we mean by nanobiology. So nanobone itself consists of nanocrystals of hydroxyapatite, and these wafers are basically maybe 3 nanometers by 50 nanometer wafers, and I'll show a picture of that in the next slide. And we chose that size actually has the same. It's similar in size, chemistry, and morphology to human bone. These nanocrystals are not bound to one another. They're basically independent, and as such, because of that surface structure, proteins will absorb rapidly to the surface. But the second part of this product, which is kind of unique, is the ASG is basically an amorphous silica gel matrix. So silica gel being SiO2, it's it's basically very hydrophilic. It releases silicon dioxide, which has a very negative charge. And you got to remember that this ASG surrounds each and every wafer of the hydroxyapatite. So you have basically a very robust mechanism. And what happens is that this amorphous silica gel matrix will transform into an organic matrix because the silicon dioxide will attract proteins. Proteins, as you know, are all pretty much positively charged. And I'll go into that a little further. Let me have the next slide. I just want to show some pictures of this. So there you have the nanocrystals of HA, which is the white, embedded in that amorphous silica gel matrix, which is the blue. So all of them are bound together. Now you got to remember that organic matrix, that silica gel matrix, is very porous, so that you get a lot of blood and cells and everything that go in here, and they're actually being pulled in by the negative charge and a couple other mechanisms which might be too much to go into here. I just want to point out on the right is a magnification view. That's the Nanobone wafers surrounded by the silica gel matrix, and they kind of shape into that pine cone morphology, which is very similar to cancellous bone. Can I have the next slide, please? So what happens is, as the silica gel dissolves, it's replaced by an organic matrix, which consists of cells and proteins, which leaves each nanocrystal embedded in this, and that basically initiates the body's own remodeling process. To get down into the brass tacks, let me have the next slide. So basically, we did a bunch of staining. This was done in an animal study. You have glycans and glycoproteins, which show a lot of activity, but specifically we stained for BMP2, osteocalcin, and osteopontin. Now, BMP, everybody's aware. This produces, this stimulates osteogenesis in different types of cells. Osteopontin is a bone sialoprotein. It functions in the early phase of osteogenesis, and it really assists in a differentiation of osteoblasts. Osteocalcin is basically a specific marker for osteoblasts. So we know, with that being there, that we've got quite a bit of stuff going on. The two together, the osteopontin, osteocalcin, these are typical markers for a mineralization phase. So I think that's why you might see such early kind of mineralization of the bone graft. So that's about all I'm going to do with that.